Hello. Welcome to this on-demand presentation entitled Tips and Tricks for EBSD Sample Preparation. My name is Matt Nowell, and I'm the EBSD Product Manager here at EDAX. Before we get started, I'd like to cover a few housekeeping items. First, you'll notice the Q&A widget at the bottom of your screen. You can use this to submit your question. Because this is an on-demand webinar, these questions will be submitted via email and answered as soon as possible. Additionally, you can find a copy of today's slide deck in the resource list widget that looks like a green folder at the bottom of your screen. To outline what we're going to cover today, first I'm going to talk about EBSD pattern quality. Then I'm going to go into mechanical polishing and the steps involved. I'm going to cover electro polishing and then different types of ion polishing. And then I'll conclude today to talk about non-conductive samples. First, I'd like to acknowledge a number of different people who have helped compile this presentation. First, Ron Witt from EBSD Analytical, George Vandervoort from Struers, Jeff Fair from BYU, Joe Michael from Sandia National Lab, and then a number of different commercial entities which are heavily involved in sample preparation: Allied High Tech, Bueller, Fishione Instruments, Gatan, and Joel. This slide shows an EBSD pattern for what I've called traditional polishing, which is generally mechanical polishing down to something around a 1 micron final abrasive. And in this material, it can often, in most materials, often will produce good EBSD patterns that are very indexable. We see diffraction bands there. We can detect them with a Huff transform. But if we look at mapping this area, you'll notice here on the map of the left is the image quality map, where we see some grains that occur as brighter spots and that give us good diffraction patterns, and areas that are darker that do not give us as good as diffraction patterns. And if we look at the map on the right, which shows us an orientation map where the good data is colored and the bad data is not colored, you'll see that the percentage of points that we can index with high quality is lower than what we'd really like. And the reason this is polishing quality. So if we look at an EBSD pattern from the same material, and this is a zirconium oxide sample here, and we adapt our polishing routine to what I'd call an EBSD-specific polish, we see that the pattern quality improves. And in the pattern here, the bands become a little bit sharper. We can still index just as well, but the quality of the diffraction has improved a little bit. And now if we look at the image quality map on the left, rather than seeing some bright areas and some dark areas, we actually see resolved grains that appear clearly. And in the orientation map, we see that nearly 100% of the points are indexed with high confidence. And this is more of what we want to get when we polish an EBSD samples. We want our yield of usable diffraction points to become closer to 100%. And so here, if we compare the traditional polish on the left with the EBSD polishing on the right, you can see that the sharpness of the diffraction increases. We see a little bit more detail in the bands. We see some higher order bands in the pattern. And this is just due to the improvement of the polishing. And so on the very top layer of material where the EBSD patterns are formed, we have less residual deformation, and our diffraction conditions are just more strongly met, and we get better diffraction. And this compares the actual map on the left, where we get a lower indexing rate, with the map on the right with EBSD polishing, where we get nearly 100% of the points correctly indexed. So clearly, if we prepare a sample with EBSD in mind, we can improve the quality of our final results and get a more accurate representation of the material microstructure. Now, before I go much further, I really want to point out that I come from an EBSD characterization perspective. I wouldn't really say I'm a sample preparation expert, although I have a lot of experience preparing samples for EBSD. But the folks who really know the most about this are the people who provide sample preparation equipment and consumables, and companies like Allied High-Tech, Buehler, Struers, all can help guide preparation for specific materials and specific type of applications. Other good references for this include George Vandervoort's book Metallography, Principles and Practices, published by SM. There's also a couple of nice papers by Katrakova and Muklik from around 2001 and 2002, which give some specific recipes for a wide range of materials. So now that I've shown EBSD patterns prepared generally for metallography and also specifically for EBSD, a concept I'd like to touch on is the idea of subjective evaluation, which is it's difficult to judge an image for quality when it's a subjective evaluation. So the analogy I like to use is put up three paintings and say, well, which one's best? The idea is when we look at EBSD patterns, it's often difficult by eye to judge if it's a good pattern or a bad pattern or which is better. And so while it's nice that EBSD patterns look nice, we have to remember in the end what we're trying to do is index them correctly and reliably. And EBSD patterns can look differently depending on what type of processing we've used to display them. And so this is just an example of an as-collected EBSD pattern. So this is actually just the live raw image coming from the phosphor screen with the detector inserted. So you can see as we see a diffraction pattern, but we also see that there's a strong intensity gradient. It's stronger toward the center, the lower center, and then it decays radially. And it's generally low contrast compared to what you'll sometimes see. And that's just what you actually see based on the distribution of the electrons coming out of the sample and impinging on the phosphor screen. Generally what we do is we do some sort of a background correction. So we take an average intensity gradient from multiple different grains with different orientations to blend out the spatial information. We save that as a background, and then we either subtract it or divide it from the live image, and we get a pattern that looks like this. Is what we call a background corrected EBSD pattern. So that intensity gradient has sort of been normalized away, and the contrast is improved, and this type of pattern is generally pretty easy to analyze with the band detection algorithms and determine the correct orientation. However, in some cases, it can be difficult to collect a background. The most obvious example is a single crystal material. So in that case, what we can do is we can take a pattern and then blur it with a blurring filter, multiple passes of a blurring filter, and use that blurred image as a background. And we call this approach a dynamic background correction. This just shows an example of a dynamic background where in this case, 128 passes are used, and you see again, it's removed the intensity gradient and provided bands that can be detected via the Huff transform. And then finally, if you really want a nice-looking pattern, you can do some different image processing routines. This is an example of combining both the regular and the dynamic background correction together. You can see a little bit more detail in the pattern, a little bit more contrast. And we can take that same pattern now into something like Photoshop or ImageJ, where we can adjust the contrast, adjust the brightness, and really sort of optimize the pattern for visual appeal. But again, it's important to note that this isn't really necessary for the band detection and indexing part of the analysis. So if we put these all together, you can see, basically what we want to do is get away from the as-collected image where there's a strong intensity gradient and low contrast, and get to some amount of processing which will show a flat-fielded image with contrast that allows us to detect the bands correctly. And that's really, when we talk about indexing and preparing a sample, we're not worried too much about what we need to do to get a pretty pattern. We want to be able to get indexable patterns reliably across the representative surface. So I mentioned the surface is that, generally when we think about preparing a sample, we're gonna flatten it out, but it's not really a requirement for EBSD. It just increases the yield of patterns that give us EBSD patterns. So this is just an example from a zinc coating on steel, and you can see on the left in the SEM image some crystals, some faceted crystals. And we look at the map there on the EBSD orientation map on the right, and you can see from that sort of as deposited surface, we get usable EBSD patterns from about 2/3 of the points collected. And the points where we don't get patterns are basically a point where the beam hits the surface, but there's not line of sight from that point to the EBSD detector. It's just blocked by the topography of the sample. And so while we can analyze rough surfaces, and in some cases it's required, we can improve the yield of samples by flattening it out to reduce these topography effects, while at the same time removing deformation. So this is just a little schematic, and I've called this an EBSD urban legend. But you can take a material and you can put it in the SEM, and you can put the beam on it. And if you look hard enough, you'll often find some sort of a diffraction pattern. So here you can see a pretty weak diffraction pattern, but it's certainly indexable. We see a little bit of an artifact there to some amount of topography. And this is just from a coin I took out of my pocket and threw it in, and I could get a diffraction pattern. And so, sample preparation is not always required to get a pattern. But if we click around the surface of a coin long enough, you see some areas there on the left we get a pattern. Other areas we get areas that suggest a pattern. Other areas we see are a little bit harder. And this is obviously designed to be a little bit humorous, but you can spend a lot of time clicking around to find a pattern for analysis. And if we were to try mapping, our results would be a little bit different. So this is a map from a section of a quarter, and we look at it. We see the SEM image on the left, the EBSD image quality map on the right. And when I show you the points that we can index, you see there are very few of them we actually index with high reliability. Is that without preparation, we can get sometimes patterns, but we don't get reliable mapping. But if we take that same material, we polish it, we then see with our EBSD results, we see grain contrast, we see orientation contrast, and we get a representative view of the microstructure rather than just a few patterns here or there. So when we talk about preparation, our goal is to produce a representative flat surface, and we want to minimize the introduction of deformation and remove what deformation we can that's caused by the preparation to optimize EBSD pattern quality and yield, which allows us to really characterize the inherent microstructure. So as we talk about what we need to do to prepare a sample, I'm going to step through what I've called an all-purpose preparation procedure. And so the terms I'm going to use are generally the same as we talk to different sample preparation companies. What we're going to do is we need to talk about how we choose our sample, how we section it, how we mount it, and how we grind and polish it, and then the final polishing. And these steps are comparable for all sorts of different materials. And basically we're starting at a large sample, working our way down to a final polish. Now, one of the most important concepts when we talk about sample preparation is the idea that it's all a balancing act. We have to balance a number of variables. Often one of the most important is cost, what quality of results that are required for our analysis, and then the time we want to spend preparing it. And the same thing we can look in terms of how many samples do we need to prepare, what kind of throughput do we need to be equipped to handle, what sort of consumables do I want to have available, and what's my budget for that, and what sort of equipment do I need or want to handle different types of materials. And so the idea of the number of samples you're going to analyze, the budget you have, your lab space, and what's your acceptance criteria for your final results can all influence sort of your approach to how you would equip a lab and how you would use that equipment. And so what I'm going to present is sort of the approach that we use in our lab, where it's heavily biased towards mechanical polishing, and I'll give examples of why that is. So the first step is to section a sample. Usually you start with a larger piece of material, and you're going to section it down into something that's going to fit nicely into an SEM. With EBSD, of course, we have to tilt the sample to around 70 degrees, so we generally use smaller pieces, and sometimes you look at flat. And as we sample a material from a parent piece to a smaller piece, we really want to minimize any microstructural changes that are going to occur due to the sectioning. And so the two most common methods are usually a high-speed abrasive saw or a low-speed diamond saw. Really, I'd say for EBSD, the low-speed diamond sectioning is preferred because it minimizes the deformation that's introduced. However, using a diamond saw, of course, will take a little bit more time than a high-speed saw. And this is just a little schematic. This is from the ASN handbook, where it shows the depth of deformation introduced with an abrasive cutoff wheel and also with a low-speed diamond saw. And you can see that in cases of these different materials, we have copper, a couple of different steels, and titanium. The diamond saw introduces the minimal amount of deformation. And that's important because whatever deformation we introduce, we then want to remove with the subsequent sample preparation steps. So by minimizing this, it's basically easier to remove and less room for error going forward. Now, mounting, it's important to note that when I mean mounting is first what we do is we're embedding the sample into some sort of a mounting material that makes preparation easier. And so that's not always necessary or required and will depend on the type of equipment you have. But for the equipment we have, it's easiest to prepare the samples by mounting it into the little mounts. And so there are really two main classes of mounting. There's sort of the compression hot mounting, and then there's the more cold or castable type mounting material. I've put here my preferred method is to use compressive mounting. I do this in conjunction with a resin that contains a conductive filler, and the reason for that is just to help manage the flow of electrons from the electron gun to the sample to ground to minimize charging effects. And we'll talk later in this presentation about charging. And so by using a conductive mount, I'm hoping that helps minimize charging effects. However, it's important to note that not all samples are going to be able to take the pressure and heat of a compression mount. I've certainly had experiences of accidentally recrystallizing a few heavily deformed materials using a hot mount material at 160 C. And so in those cases, a castable epoxy can be used, and it has a lower curing temperature than some of the hot mounting materials. And so no matter what we use, we want to make sure there's an electrical path to ground from the sample to the SEM ground. And so you can use conductive paint, conductive tape, something to make sure that we have a path to ground because we don't want the charging artifacts. This just shows for hot mounting sort of the idea of what happens is we start heating up the material, it then flows around, and as we put pressure and temperature on it, it will cure into a hardened material. This is a thermosetting material. This is a material that minimizes charging. It can also be used for electro polishing. The important things to note here is you really want to have a clean sample before you go. It helps to improve adhesion of the material to the sample. And it's fast and it's reproducible. I can put a sample in our hot mount press, and in about 10 minutes I have a sample that I can take to the subsequent step, compared to some curable epoxies that can take hours to multiple hours. Now here, when you read about the different steps involved in preparation, you often read, differences between grinding and polishing and their different steps. Personally, I conceptually think of them about the same thing. And then in general, in both cases, we're using abrasive to remove some amount of material from the surface. But while we're doing this, we also introduce a little bit of deformation onto the surface. And so what we want to do is we want to start with an initial step of some size of abrasive, use it to get a homogeneous layer, and then step to smaller abrasives, which will then remove some of that initially introduced deformation and shrink the size of the deformation layer. So this schematic here, this is from a LECO handbook, kind of shows schematically as we go from fine grinding to rough polishing to final polishing, the idea that the outer layer becomes smaller and smaller, and the deformation layer becomes smaller and smaller. And so all we're trying to do is minimize the size of both of those at the end of our polishing procedure. And so when I talk about grinding, basically I define this as when I'm using silicon carbide abrasives embedded into a paper. And so I think silicon carbide paper is probably the most popular abrasive for grinding because it's high hardness, good cutting, and relatively inexpensive. You should use some sort of a lubrication to minimize the heat input and keep the abrasive clear. I commonly use water for materials that will tolerate it. Really, one of the most important things is that these silicon carbide papers have a finite lifetime. They're called consumables for a reason. And so we only use them for 30 seconds each before we call them finished. Then we'll switch to a new paper. And that's something we learned and we found to be very effective, is that by replacing and using a new paper, we get more efficient polishing. We actually get better results in less time. This is just a kind of a classical image showing that at each step, you see that the grinding marks with each decreasing abrasive size become smaller and smaller until as you get to some of your final steps with diamond, that the scratches go away. And that's kind of what we're aiming to do with polishing down, is that the feature size of the damage introduced with the different size abrasives becomes smaller and smaller. But I'll show some examples how even with these areas where we can no longer see them optically, we can still detect microstructural changes being introduced using EBSD. When we talk about polishing, basically how I define it is that rather than having an embedded material into a paper, we select a cloth and we select an abrasive. So we have a little bit more flexibility in terms of how we mix and match things. And so when we talk about abrasives, diamond is obviously the hardest abrasive, has the best cutting performance, and it's generally one of the more expensive ones. And so alumina, which is still pretty hard, is pretty commonly used. It's what we generally use for most materials. And of course, for the polishing cloths, there are a wide selection available. The one I use is what's called Imperial cloth. It's from Allied High Tech. And it has a few things that I like. Is first, it's all-purpose. I can try it on many different materials. It's low napped, which helps minimize surface release. But there are all sorts of different cloths that are available. And if you look on different websites, they will give potential applications for different cloths, and I'll give an example of this in a little bit. The one on the bottom there is the Chempol cloth. This is one that's designed for colloidal silica, which is the solution generally used for final polishing for EBSD. And so, I generally tend to start with an all-purpose cloth. I keep more of those in stock as consumables and try them on more sorts of materials, and generally go to more specific cloths when necessary for my preparation. A common question I get is, sort of how hard should I push when doing this and for how long? The general rule of thumb is that as you increase the pressure, your material removal rate increases, but at the same time you introduce more deformation. So generally I've called these lighter loads as I aim for 5 to 10 pounds force on a sample, and I'm generally using 1 inch to 1 1/4 inch samples in my polishing procedures. And so generally like to polish for minimal times. It's all relative to reduce artifacts. Again, different vendors can offer very specific recipes for materials. What I'll present is my general purpose recipe. I'll show examples where it's worked pretty well. But if you want to try to optimize from that, there are resources to go to. And again, like I showed in that previous slide, for coarser abrasives, you can use an optical microscope to sort of watch the homogeneity of the scratches. I personally don't do that. I go from one step to the other and trust that the procedure is going to work. And mostly I clean my sample between each step so that I don't have any residual older abrasive that would throw off that approach. One of the key points for EBSD is the final polishing step. And my first bullet point here basically sums up a lot of the philosophy, is that a good final polish can make up for a lot of things going on in the previous polishing steps. And so the solution that's used and recommended is the colloidal silica. And I've put here usually a 0.05 micron size. I'll give an example where we use a 0.02. I'd say usually 0.05 generally because it does pretty well and it's less expensive than the smaller abrasive. And it's a good polishing medium for EBSD. In this case, the silica particles, they're in an alkaline medium. The important part of that is that it has a pH value that produces a chemical-mechanical polish. So as we polish, we also have a little bit of a chemical reaction that really helps minimize the final deformation layer thickness. It basically removes that little bit of deformation. It is possible to adjust this action chemically. Some people will add some chemicals to adjust that pH. Generally not something that I do, but you can see references to that in the literature. And when you use colloidal silica in conjunction with a vibratory polisher, you can use it for a few minutes to a few hours to really produce some really nice EBSD patterns for most materials. So to show you now specifics for this process, what I want to do is go through a case study of an Inconel 600 alloy. This is a nickel-based superalloy where we've sectioned them into little pieces. We've mounted them into 1-inch compressive mounts. And what I'm going to show you, patterns collected at about 1K pixel resolution, imaged with EBSD at about 100 by 100 pixel resolution and about 80 points a second. And to give an idea, I started with 240 grit silicon carbide paper, stepped through from 240, 320, 400, 600, 800, and 1200 grit papers, used each paper for 30 seconds, used 10 pounds force and 150 RPMs using water. After those grinding steps, I switched to using the imperial cloth, using 1 micron and 0.3 micron alumina for 10 minutes each at 9 pounds force, so a little bit less pressure, and 130 RPM, a little bit less speed, and using a water drip. I didn't want to completely flush away the abrasive, but I'm trying to keep it a little bit clean. And then I go to colloidal silica, again on an imperial cloth and a vibratory polisher, starting at 15 minutes, going to 4 hours. And what I want to do now is sort of present those results. So this pattern here on the left, if I convince you to squint a little bit, you'll see there's a very faint EBSD pattern. If we look on the right, the forward scatter detector image, we really don't see much microstructural contrast. We see more the topographic contrast introduced by the polishing. And so, when we're transitioning away from grinding, really we're not at a point where we get much EBSD with just grinding. When we show the results after 10 minutes of 1 micron alumina, now we see an EBSD pattern is very clearly visible on the left. And at the forward scatter detector image, we start to see a little bit of grain contrast within the microstructure. Here with 0.3 micron alumina for 10 minutes, the pattern again is visible, a little bit better grain structure, but now the concept of, I'm going to be comparing patterns by eye, which one's better, becomes a little bit trickier, and so we'll step through these. This one's now using the 0.05 micron colloidal silica, 15 minutes, really improved contrast in the FSD image. This is now 30 minutes with colloidal silica. I've still put improved contrast, but it's a little difficult to really see visually. This is now 1 hour of colloidal silica. You really see fewer scratches now. We're kind of removing that final bit of deformation. This is now at 2 hours. You can see we get pretty strong contrast. We are also starting to get a little bit of topography. You see some of the grains are a little more recessed relative to some of the other ones. And this is after 4 hours of colloidal silica polishing. In this case, we'd say it looks like it's a pretty pristine surface for EBSD. And so it's one thing to kind of see them one after the other. But if we put all the patterns together on a single slide, it's easy to see the improvement from 1200 grit to 1 micron. And I think it's relatively easy to see the difference from 1 micron to 0.3 micron alumina. Beyond that, it can be pretty difficult to tell by eye, and that's why I talked about paintings and subjective evaluation to start. Because what we want to be able to do is go beyond a subjective evaluation. We want to use some of our metrics to actually quantifiably determine how good a diffraction pattern is. So the method that's often used is to use what's called the EBSD image quality result, or IQ result, which is just a measure of the brightness and sharpness of the diffraction bands detected with the Huff transform. So if we plot the image quality map for each preparation step on the same scale, so the dark points here would have low image quality, the brightest points have the highest image quality. You'll see as we step through the preparation procedure, the image quality values improve. This is sort of what we'd expect. We're improving, we're minimizing the deformation layer, we're improving the quality of the diffraction. And if we then show, instead of showing the maps, we show this on a chart, we see normalized image quality here, that as we continually polish the surface, we see an improvement in image quality value up until we get about 2 hours of colloidal silica polishing. Then it starts plateauing. Going from 2 hours to 4 hours didn't really make much difference in image quality. It's important to know with image quality, it's a function of a lot of things, and we tried to keep as many as we could constant. It's a function of camera settings, of beam current, of orientation, so we sample a lot of grains. But by using an average, we can clearly see the trend that's occurring as we prepare the sample step by step. But when we look at this, if we show that 1 micron pattern and we show our 4-hour colloidal silica pattern, sort of what we saw the initial part of the presentation is both of these patterns are indexable. We can detect the bands and we can determine an orientation with high confidence. So what we want to know is what percentage of the points can we index at each step. So if we show this, again, with silicon carbide, we're only about 5% of the points are usable. That was about as well as we did with the quarter. Jumps up to about 80% with 1 micron alumina. And then past that, it jumps up to about 98% with 0.3 micron alumina. And then it jumps up to the 99 or greater percents once we start going to colloidal silica. So that, for a lot of our analysis, once we go to 15 minutes colloidal silica, we're really going to get sort of what we need for a lot of our microstructural characterization. Clearly, if we're going to just try to measure grain size or texture or phase, a little bit of colloidal silica is probably going to get us pretty close to where we need to be. And if we put these on the same chart, you can see that with image quality, we didn't start plateauing until about 2 hours of colloidal silica. But if we look at indexing rate, we really are where we need to be, with 15 minutes. However, in some cases, we may want to measure deformation. And so this is being measured here, plastic deformation, what we call our CAM, or kernel average misorientation measurement. This is a measurement that just looks at the small changes in orientation that are occurring. And so if we look at this here at our 1 micron, our average CAM is 1.6 degrees, drops down to 0.83 with 0.3 micron, and then goes to 0.65 after 15 minutes, about 0.5 after half an hour, and then jumps down to about a half a degree after an hour or so, and sort of plateaus there a little bit. But it's the idea that a good final polish really starts to work at about 1 hour. And so if we show this, all three of these metrics on the same chart, you can see generally if you aim for about 1 hour of colloidal silica, you'll generally be in the neighborhood. And so Obviously, this is for a nickel superalloy. It's a relatively easy sample to do for EBSD. But the same methodology can be used on all sorts of materials if you really want to optimize things. But it gives you an idea of what you would look for different materials, image quality, indexing rate, and misorientation to get an idea of is your preparation good enough for what you're trying to measure? And generally, if you're worried about deformation measurements, you might have to do a little bit more polishing than you would if you're just interested in texture type measurements. And this is just a kind of an interesting little slide. This is taking a surface, polishing it, and then cross-sectioning it, and then polishing the cross-section down to our final polish so that we can actually see the deformation layer that's introduced during different grinding steps. So the map on the right there shows 240 grit silicon carbide. The polished surface is sort of on the middle right of that. And those warmer colors, the yellows and greens there, show the deformation layer that's introduced with the 240 grit silicon carbide. We polish that down to 1200 grit. Again, and this time it's flipped, so the polishing side's on the left-hand side of that image on the right. And we see the layer on the same scale at 1200 grit is now much smaller and localized at the surface after those additional grinding steps. So this is kind of just a neat picture to show how EBSD can measure the damage caused by polishing, and also just to give an example of how EBSD can measure that plastic deformation. So at this stage, I really just wanted to summarize what I've called my generic EBSD polishing recipe. Again, I start with 240 grit, step through 320, 400, 600, 800, 1200, 10 pounds force. Here I use complementary rotation. What that means is both the platen and the samples are rotating in the same direction at 150 RPM. Now, it's important here to note that I'm using a sample where I can control the rotation speed, I can control the pressure, and that's one of the parts where we select material. It's certainly a lot easier to give a recipe where I'm giving you a very specific force to use compared to try to hold it with your hand in place with constant force. Generally the equipment's going to work better than hand polishing for consistency. Now with this recipe, now I generally use 1 minute for each grit size, but I change the paper after 30 seconds. And that's, again, just to have a fresh abrasive, make it efficient. And then use water lubrication in general to keep the abrasive cool and clean. Stepping the next part, again, is starting with 1 micron and then 0.3 micron alumina suspension on this low nap synthetic rayon all-purpose cloth, which is the Imperial one from Allied High Tech. This I go to the 9 pounds force, but now I use contra rotation, so the platen and the samples are rotating in opposite directions, but at 130 RPM. But it should be a little bit more efficient in terms of material removal, but less removal rate due to the smaller abrasive sides. The reason I do that is that with the more coarse abrasives, if I use contra rotation, it's a little bit easier for my machine to sort of introduce a little bit of a bevel or a non-planar from front or back surface onto the sample. And ideally, I want my back and front polish surfaces to be parallel because it helps keep my sample at the correct orientation of what I expect. But I can switch to the contra rotation at this stage because I'm not going to be removing as much material with these smaller abrasives. On these cases, I moisten the cloth with water, and then I go to a slow drip just to kind of keep it cool and clean, but not remove the abrasive. And I periodically just refresh the abrasive 2 or 3 times in that 10-minute span. And then I'll go to a vibratory polisher using the colloidal silica, generally for around 2 hours. If you don't have a vibratory polisher, you certainly can replicate this just using a wheel and a sample. You just have to keep solution on there for that sort of a time, so you can drip it on. The vibratory polisher is nice because you just put the sample in a tray with the cloth and the solution, and it just keeps moving with a little sample weight until you take it off. So this slide just shows the result of this preparation procedure on a few different materials. That's some titanium there on the left, a duplex steel in the middle, and an aluminum extrusion there on the right. So on a range of materials, it generally works pretty well. And so this is the procedure we use when we look at samples. It's the procedure that Ron Witt uses when he does some of his samples for his lab. And it's one we've sort of converged into through years of doing samples, and it works pretty well. So now what I want to show are sort of some of the off cases, is when we want to do something a little bit different. And so this is just an example of an alumina sample. So alumina is a ceramic. It's obviously a lot harder than the metals. It doesn't deform quite as ductily as a metal would. And so what I did here is on the image on the left, I polished it down using 0.3 micron alumina. So I'm polishing alumina with alumina. And on the right, I polish it with diamond. And so diamond is a little bit harder than alumina. If we compare those images, we see that, yeah, sure enough, it is a little bit flatter with diamond. But what's interesting is that while the image quality is a little bit better using diamond, the percent indexed is still about 69% for both. And so I think that's partly just due to the fact that it's a generally brittle material, and that even though it's not flat, we're still getting indexable diffraction patterns for about the same percentage of the time after this polishing step. Ideally, the rule of thumb is an abrasive should be 2 to 3 times harder than the sample material. Obviously, for something like alumina or polishing diamond, that option may not be available. But now if we take our alumina result and we then polish it with colloidal silica, so we're not only polishing, but we're also using a little bit of a chemical etch, then you see that our surface becomes quite a bit flatter, and we get an improvement in indexing rate of about 85% into a sample that has some pores in it as well. And so you can see we can start to see the microstructure. And so generally for hard materials like alumina, I'll use something like a diamond suspension or a lapping film to polish before the final polishing with colloidal silica. When you do that, the polycrystalline diamond is generally more effective, has more cutting surfaces. It usually will polish takes a little bit longer because you're having to polish on colloidal silica, remove material with longer time. The removal rate's not quite as long. So in this case with alumina, I did 4 hours. Other approaches like thermal etching have been used, but this will sometimes cause things like grain boundary grooving, which will cause a topographic effect, which is again block the EBSD pattern and reduce your indexing rate. This is just an example from a pure metal. This is pure copper. In this case, it's softer than an alloy. It's a little bit more susceptible to surface smearing and deformation. So in this case, I've used a 0.02 micron colloidal silica, and that generally works pretty well. And so, again, the reason I usually don't use 0.02 all the time is this consumable is just a little bit more money than the 0.05. So I sort of use this on demand, but for pure metals or for materials that are heavily deformed. So basically with heavily deformed, what I mean is that there's, on the scale of the abrasive, there's a change in lattice curvature. There's some deformation. So I want to minimize deformation caused by sectioning so that my EBSD can actually pick up the real deformation structure in the material. Now, one of the more challenging types of samples for EBSD preparation are multi-phase samples. And the reason that is just that when you have multiple phases, you're going to have phases that have different material removal rates. So as we polish a sample, you're going to get topographical type effects. So this is just an image on the left of a copper oxide, aluminum oxide reaction region. And so if we're looking at it sort of in a traditional flat SEM view and looking straight down at it, we see the layers nicely. But when we tilt it on the right for EBSD analysis, we can see little hills. There's that center area is higher than either material on the side, and there's little slopes going down between that. And so when we look at a particular grain structure, we look at it flat, that kind of shows us what the structure looks like. But when we look at this tilted, because the sample is not just tilted to 70 degrees, but there's also a tilt sort of orthogonal to that, our beam is not going exactly where we think it's going, and so it distorts the microstructure. And so for texture and phase analysis, that's not going to be important. For any morphological grain size, grain shape type measurement, that's going to be a problem. So this is just a nice example of a multi-phase material to try to prepare. So it's a solder sample, so you have a tin and copper interface. And so for this case, I kind of asked Allied High-Tech what they'd recommend. And so they came up with a specific recipe that's shown here with specific abrasives, specific cloths, specific times and pressures. And so what they're able to do here is target specific approaches that should, in this case, we said we wanted to minimize deformation, make it as flat as possible for these materials that are different hardnesses. So when we look at the patterns from each phase, you see we get indexable patterns from each. And so they're not perfect patterns from each one, which we'd generally like if we were looking at a single-phase material, but they're usable patterns for each phase. And so, a lot of times for multi-phase samples, the steps we use, we need to minimize the topography that's introduced while still getting usable diffraction patterns. So the pressures are lower, the polishing times are less, specific cloths for specific types of materials, specific removal rates, and we're trying to minimize the final polishing time with colloidal silica to minimize differential etching rates with the colloidal silica medium. And this just shows on the left the orientation map, and on the right the phase map from that interface in the solder material. So using this approach, we still get very nice usable results with EBSD mapping. So in summary, this is what I've just titled this, Miscellaneous Thoughts on Mechanical Polishing. Mechanical polishing can be used to produce excellent EBSD patterns and good EBSD-OIM mapping data. It's the method we use for probably 90% of the samples we need to prepare. Part of that's by choice, part of that's just based on what we have available. For most material, alumina suspension works well. I use diamond only for high hardness or when I need to make sure it keeps flat. As I mentioned earlier, keeping the front and back sides of a sample mount parallel is important, particularly if you're going to do something like large area combo scan mapping. And I've said don't be afraid to spend on consumables to get good results. Be a little afraid not to. Is that they're consumables for a reason. I don't have any vested interest in a consumable company, but I've tried preparing where I've tried to save on consumables, and certainly I end up spending more time in the long run than if I use fresh consumables. So another approach we can use to prepare samples is electro polishing. That's where we take a sample, we make it an anode in an electrolytic cell. To do this, we have to choose the correct solution to use. The sample also has to be conductive, and so that's where hot mounting can be useful for electro polishing. It's important to note that the polished area is often smaller than the actual sample surface, and that the polishing quality can change as a function of position. And you still have to do some initial polishing down to, say, 1200 grit silicon carbide as an initial step. And so you can see in the schematic, you have your sample as the anode. You have it in applying current and a voltage here with the solution flowing across the material to remove layers of material from the sample surface. And so with electropolishing, it can work very well. And this is an example from an aluminum foil. So we get a nice pattern, nice maps. And sometimes not so well. So this is, again, an aluminum alloy, but here we see some porosity on the surface. We see our indexing rates on the right are not as high as we saw in the previous example. And so while EBSD can give great results, there are a lot of variables that need to be controlled. The surface area ratios, bath agitation, the temperature and the age, your current density, your polishing time. And you can see on these curves, depending on which solution you use, you have to make sure you get in the right regime so you're polishing and not etching and not in a gas regime. And so I don't have as much experience with this. Generally, labs that look at the same type of materials over and over again can come up with a good electropolishing routine. but some of these solutions are poisonous, corrosive, or explosive. So personally, we're not allowed in our facility to have some of these chemicals. So we don't have a lot of experience doing this, but we've seen plenty of examples of it working well, and certainly a few examples of it working not so well. Now, another growing application is the idea of using ion etching, and either broad beam or focused ion beam approaches, where basically we accelerate an ion of a material into the surface to remove material from our sample. So this is just a little schematic. You know, our ion comes in, it blows some material off, but of course, I tried to show schematically, it also forms a little bit of an amorphous layer. So as we do this, the angle of attack that ion comes in will play a strong role in terms of the removal rate and also the deformation and amorphous layer that's residual, as well as the energy of the ion. And so this is just an example of a magnesium sample. This is a magnesium friction stir weld that we etched with a broad beam source at low voltage, 2.5 kV, to get the patterns. This is an example of a cadmium telluride solar cell. So when this is first deposited, there's some significant topography. We can see that on the right. The black areas are areas where the beam's blocked. So again, we went in at an almost grazing angle, about a 10-degree grazing angle with a 2.5 kV broad beam etch to sort of smooth out the surface. And you can see that our indexing rate went from below 50% to around 90% after some ion etching. The residual black areas there are pores in the film. And we also use broadbeam ion etching to remove passivation layers from copper interconnect lines. So on the left there, you can see the interconnect line with about a 100 nanometer, 1,000 angstrom silicon nitride passivation layer. So again, going in with a glancing angle, remove that passivation layer, and then we can see we get nice orientation maps from the different size lines in the structure. And those are all examples of materials that can be tricky to do conventionally. This is an example from a cast aluminum silicon alloy where ion etching, broadbeam ion etching, is just used as a nice final step to improve the quality. And so this is one that we prepared with our mechanical recipe, and then the ion beam preparation was used as a final polish to just improve the final results. And so this is a dual phase sample. It just helps clean up the final results very nicely. This is using the Fiscione SEM mill. And then in addition to using this for surfaces, we can also do cross-sectioning. So this is an example from the Joel cross-sectional polisher where the ion beam can go straight down against the surface. It's blocked using a shielding plate, so it goes in basically perpendicular to the sample surface of interest. So we're not introducing as much direct energy into the ion into the crystal lattice of the material we're interested in. So you can see we get nice channeling contrast on the image on the right there, and we also get very nice EBSD results. So this is a result from a gold wire bond sample, and so this would be very difficult to prepare for EBSD conventionally. The ion beam cross-sectioning is a very good alternative. We can also use a focused ion beam or a FIB to prepare samples. So in this case, we have a focused beam of gallium ions. We're able to do things like position the sample for milling or cutting, and then position the sample in situ for EBSD. The advantage of this is we're able to prepare the sample in vacuum for something that may be reactive to the atmosphere. We're also able to prepare things on a very small localized scale. So, this is just a schematic of a couple of different approaches. We can prepare things towards the edge. You can see on the left there we're cutting down into a surface similar to what we saw on a cross-sectional polish. The difference is there we're also creating sort of a wedge fanned outward so that we have line of sight from our analysis to our EBSD detector, so we're not blocking our signal. We can also go onto the top section of a surface where we do something called a low incidence surface milling, where we come in at near grazing angle to a sample surface, and that allows us to look at an area, and again, we have to make sure we avoid shadowing. So this is just a result wanted to show to compare to our earlier gold wire bond. This is prepared on a fib. So we can go in very locally and prepare just that particular area, so the preparation time's less than we'd get with a broad beam source. But with fibs, we can also go in and do very specific areas on a small scale. And these are some very cool crystals, courtesy of Joe Michael at Sandia National Laboratory. These are zinc oxide crystals, sort of form these balls, kind of look like a porcupine ball. And Joe has come in here and sectioned across that, and then you can see the cross section where we see the crystals growing radially from that structure, and we can see the orientations growing in different sample reference directions using the EBSD results. So ion beams are very new and efficient way of preparing samples. We want to monitor the incident angle in and the energy in to minimize amorphous damage that can be created. A couple of other things just to be aware, of course, is that the material removal rate will be anisotropic. It varies by orientation. This just kind of shows an effect here where you have in an iron silicon alloy, the 1,1 grains resist sputtering, the 0,01 grains sputter faster, and you'll see some surface topography develop if you etch that for a while, and so that topography can again block your EBSD signal. With ion beams, you can also get some funny effects. In some cases, you can cause a crystal structure to become amorphous. In other cases, you can get reactions of the ions with the material. An example here is gallium and aluminum causing issues. And in other cases, you can get the beam-induced phase transformations, where the energy of the ion beam can be a driving force for a transformation of material. Now, I want to wrap up talking about charging. And the idea here is even if we prepare a sample and we get nice patterns, if we can't put the beam where we want it to be, we can get some pretty ugly-looking maps. So this is just an example from a zirconium oxide ceramic, where if we look at it with the SEM, we sort of see your classical charging and blooming effects, and we try to map it. You see we get, coherent colors and grains, but we see some funny, jaggedness and repeatedness of charging, where basically we get a local buildup and then a discharge of the charge, and the beam's just not going exactly where we think it's going to go. So what can we do to minimize this charging effect on non-conductive samples? One of the easiest things to do and traditional things to do is to put down a conductive coating. And so generally I recommend a carbon coat over something like aluminum or gold palladium. The reason is that carbon has a lower atomic number, so it's not going to scatter the electrons coming out of the diffraction as much as a gold coating would. And so this just shows the effect of pattern quality by coating thickness. So there's a pattern with no coating and going up to 50 angstroms of carbon. You see, we still see a decent diffraction pattern, and this is from an alumina substrate. And this just shows our indexing rates for a material, how as we put a thicker and thicker coating in, our indexing rates start to drop off after a while. So generally we aim for about 10 to 20 angstroms of carbon, enough to dissipate a charge, but not enough that it's going to start to interfere with our indexing performance. The problem with this, of course, is you have to be able to control the coating thickness. And so we use an instrument that has a thickness monitor. Sometimes you have to experimentally figure out how to control that thickness. And this just shows the effect of coating on your SEM image. So if we get between that 10 to 20 angstroms, we generally get enough that we're moving the charging but still get usable EBSD data. And this just shows the effect of coating thickness on our image quality using both an alumina and an Inconel nickel superalloy substrate. So, the heavier the substrate, the stronger the pattern coming out from a higher backscatter coefficient. But in this case, it's we still get reasonable patterns at that 20 angstroms coating thickness. And this looks at the effect of coating thickness on the indexing rates. And again, at that 20 angstrom level, we still get pretty reasonable performance compared to the baseline of no coating. And this slide just goes back to that comment of preferring carbon over gold palladium. It shows the normalized image quality as a function of thickness on a nickel substrate and also on a silicon substrate. And we can see in both cases, the carbon deposition produces, a higher image quality than a gold palladium deposition would be. And sometimes with coatings, you can go to a little bit higher voltage, so it punches through that coating a little bit more efficiently. You'll get a little bit better pattern, but it doesn't make too much of a difference. Of course, the other thing you'd want to make sure you do with a carbon coating is you want to make sure you get enough material that you can dissipate charge while minimizing any EBSD pattern degradation. Even though your patterns quality will go down a little bit, they're typically going to be good enough for your orientation mapping, but be aware there is some pattern decrease. I prefer sputtering to evaporation. That's based just on control. It's easier to repeat, and it's easier to repeat from one sample to the other. Again, that's very equipment dependent. And then no matter what you do to your sample, you want to make sure from your coated samples to still have a path to ground. And so if that's conductive tape, a conductive mount, conductive paint, it's still necessary to make sure that your charge can go from your sample to ground and not disrupt your patterns. Now, another alternative to coating that's becoming more and more available to people is using the low vacuum capability of SEMs. And so by introducing a little bit of pressure into the chamber, this can help dissipate the charge on the surface as well. So this just shows the effect on EBSD pattern quality by increasing the chamber pressure from 0.1 millibar up to 1.3, where now the gas molecules in the chamber are disrupting the signal towards the phosphorus green as we put more of them in there. And you can see in this slide, this is an example where at high vacuum we're at about 99% indexing there on the left. We put in that 0.6 millibar pressure, drops down to about 97%. We go into more 1.3, it drops to 85%. And you can see that generally the indexing starts to fail towards the grain boundaries. And that's just where your pattern quality is a little bit worse to begin with. You can have overlapping patterns anyway. Luckily, typical charging can be removed with just a little bit of pressure. And so you can put in 0.2, 0.3 millibars of pressure without really degrading the mapping performance of a system. So with that, I'd just like to summarize what we've talked about today. First, sample preparation improves the quality and the yield of EBSD patterns. Generally, EBSD sample preparation requires slightly smaller and finer abrasives than conventional metallographic polishing. Metallographic or mechanical polishing can be used to prepare quite a number of samples. Electro polishing is a viable alternative. Ion beam technology allows preparation of difficult or small samples, and there are a couple of different approaches we can use to reduce charging effects. With that, I'd like to thank you for your attention and invite you to submit questions via the widget on the bottom of your screen, and thank you for your time.